Right now, as you watch this, you are moving. Not walking, not driving, not flying. You are hurtling through space at a speed that should terrify you. Roughly 1,670 kilometers per hour. That is the rotational velocity of Earth's surface at the equator. Faster than any bullet train. Faster than most military aircraft. You have been moving at this speed every single second of your life, and you have never once felt it. That is the miracle of inertia. That is the invisible contract between you and the planet beneath your feet. Now imagine that contract is broken. Not gradually, not over centuries, instantly. What happens in the next 48 hours is not science fiction. It is not a Hollywood disaster script. Every catastrophe we are about to walk through together is grounded in real geophysics, real atmospheric science, real oceanography. Researchers at NASA's Goddard Space Flight Center, geophysicists at the United States Geological Survey, and planetary scientists at institutions from Cambridge to Caltech have all modeled variations of this scenario. Because understanding what rotation gives us helps us understand how fragile everything we call normal truly is. So let us go back to the last normal second in human history. It is an ordinary morning somewhere in the world. Birds are navigating by magnetic fields that have guided their ancestors for millions of years. Ocean tides are pulling in their familiar rhythm, choreographed by the moon and Earth's spin, working together like gears in a cosmic clock. The atmosphere, that thin, almost impossibly delicate shell of gas that separates life from the void, is rotating with the planet, carried along by friction and gravity in a relationship that has persisted for 4.5 billion years. Then it stops. Not a slowdown, not a gradual deceleration over thousands of years, the kind that actually does happen naturally. Earth's rotation is technically slowing by about 1.4 milliseconds per century due to tidal friction with the moon. Scientists at the International Earth Rotation and Reference Systems Service in Paris monitor this constantly, occasionally adding a leap second to our clocks to compensate. No, what we are modeling here is the instantaneous cessation, a full stop. In the scientific literature, this thought experiment is sometimes framed around what physicists call a rotational discontinuity event. The scenario is physically impossible by any known natural mechanism. No asteroid, no gravitational force within our solar system could achieve this without first destroying the planet entirely. But as a tool for understanding what Earth's rotation actually does for us, for life, for civilization, it is extraordinarily illuminating. Because most people have no idea. Most people know that Earth rotates. They learned it in school. They know it causes day and night. They know it takes 24 hours. And then they stop thinking about it. What they do not know is that Earth's rotation is the invisible architecture of everything. It shapes the weather systems that bring rain to crops. It drives the ocean currents that regulate global temperature. It generates the magnetic field that deflects lethal solar radiation. It creates the Coriolis effect that determines which direction storms spiral. It is the mechanical heartbeat of a living planet, and every system, atmospheric, oceanic, geological, biological, is calibrated to its rhythm. Remove that heartbeat instantly, and you do not simply stop the world, you detonate it. The question is, how? In what sequence? What dies first, and what survives longer than you would expect? That is what we are going to investigate, minute by minute, hour by hour, through the lens of real physics, real science, and the kind of catastrophic clarity that only comes when you strip away everything we take for granted. Before we go further, let us establish something important. The scenario we are modeling assumes the solid Earth, the crust and mantle, stops rotating. The atmosphere, the oceans, and everything on the surface does not stop at the same moment. This distinction is everything. It is the difference between a disaster and an extinction. And it is where our story truly begins. 0 hour, 0 minutes, 0 seconds. The planet beneath your feet stops. You do not. The first 60 seconds, the great horizontal wave. You are still moving at 1,670 kilometers per hour. The ground is not. In the first fraction of a second after Earth's rotation stops, every human being on the planet, every animal, every vehicle, every building, every tree, every ocean, every cubic meter of atmosphere continues moving eastward at whatever rotational velocity corresponded to their latitude. This is Newton's first law of motion, and it does not negotiate. At the equator, that velocity is 1,670 kilometers per hour. At the latitude of London or Berlin, it is approximately 1,000 kilometers per hour. At the latitude of Anchorage or Reykjavik, it is closer to 500 kilometers per hour. At the poles, it is nearly zero. This means the apocalypse is not equal. It is not democratic. It is a function of where you happen to be standing on the morning that physics stops keeping its promises. Let us talk about what 1,670 kilometers per hour actually means when it is applied to a human body that suddenly has no ground moving with it. That is Mach 1.4, faster than the speed of sound. Faster than an F-16 fighter jet at cruise speed. It is the velocity at which the human body does not simply fall, it becomes a projectile. Every person, every animal, every loose object on the equatorial surface is instantly launched eastward with the kinetic energy of a high-velocity impact. There is no surviving this at the equator. Let us be precise about that. At those velocities, impact with any stationary surface, a mountain, a building, the ground itself after a trajectory through air, is not survivable. The human body has no biological mechanism for absorbing that kind of force. Researchers modeling similar deceleration events compare it to a collision at airliner cruise speed with zero crumple zone. But let us not look away from the physics, because the physics tells us something even more extraordinary than simple human death. The entire surface layer of Earth, the loose material, the soil, the sediment, the water, the air, all of it has inertia. All of it wants to keep moving east. And so, in the first second, you do not simply have people flying off the surface, you have a planet-wide horizontal shear event of almost incomprehensible scale. Geologists use the term shear force to describe what happens when two layers of material move relative to each other. On a small scale, shear forces create earthquakes. On the scale we are describing, the entire surface of a planet moving at high velocity relative to the suddenly stationary rock beneath, there is no geological term adequate to the task. Every fault line on Earth ruptures simultaneously. Think about that for a moment. The San Andreas Fault, the Cascadia Subduction Zone, the Anatolian Fault in Turkey, the Alpine Fault in New Zealand, the Himalayan Frontal Thrust. Every single seismic zone on the planet experiences maximum possible stress loading at the same time. Seismologists at the United States Geological Survey have calculated that the largest recorded earthquake in human history, the 1960 Valdivia earthquake in Chile, measuring 9.5 on the moment magnitude scale, released approximately 2 times 10 to the power of 23 joules of energy. A single event that was felt across the entire Pacific Ocean, that triggered tsunamis reaching Japan and Hawaii, that caused parts of the Chilean coast to permanently drop by 2 meters. What we are describing in the first second of our scenario is not one Valdivia earthquake. It is thousands of them, simultaneously, on every continent, in every ocean basin, along every tectonic boundary on the planet. The ground does not shake. The concept of shaking implies oscillation, a back and forth. What happens in the first 60 seconds is more fundamental than shaking. The crust of the Earth fractures along every pre-existing weakness simultaneously, and in many places where no weakness existed before, new fractures are torn open by the sheer forces involved. Volcanologists have a related concern. The magma chambers beneath active volcanoes, systems like Yellowstone, like Campi Flegrei in Italy, like the volcanoes along the Pacific Ring of Fire, are under existing pressure. They are held in a dynamic equilibrium by the surrounding rock. The simultaneous fracturing of the crust releases that equilibrium instantly. Within the first 60 seconds, every major volcanic system on Earth begins to destabilize. But here is what most people would not expect. Here is what the atmospheric science tells us that is even more immediately catastrophic than the earthquakes and the volcanoes. The wind. When the solid Earth stops, but the atmosphere does not, the atmosphere becomes, in effect, a planet-wide supersonic wind. From the perspective of anyone standing on the newly stationary ground, assuming they survived the initial jolt, which at most latitudes they did not, the air itself is moving east at velocities between 500 and 1,670 kilometers per hour, depending on latitude. This is not wind in any sense that the word normally conveys. The strongest wind ever recorded on Earth's surface was 308 kilometers per hour during Tropical Cyclone Olivia at Barrow Island, Australia in 1996. That wind was sufficient to tear steel structures apart, to strip vegetation from hillsides, to drive sand particles through solid wood like bullets. What we are describing is wind moving at 3 to 5 times that velocity across every surface on Earth. Every structure built by human civilization, every building, every bridge, every tower, every vehicle is exposed to aerodynamic forces it was never designed and could never be designed to withstand. The engineering concept of wind load in building codes typically accounts for winds up to perhaps 200 kilometers per hour in the most extreme hurricane-prone zones. No building code on Earth accounts for Mach 1. Within 30 seconds of the stop event, every structure on the surface of the planet at low and mid-latitudes is gone. Not damaged, not collapsed. Gone. Torn from foundations, shredded, scattered as debris moving at hypersonic velocities. The debris itself becomes a secondary weapon. Fragments of concrete, steel, glass, wood, all moving east at hundreds of kilometers per hour, impact other structures, other terrain features, creating a horizontal storm of shrapnel that scours the landscape to bedrock in some regions. In the higher latitudes, above 60 degrees north and south, the initial wind velocities are lower, perhaps survivable by someone in a sufficiently deep underground shelter. Perhaps. But even at 500 kilometers per hour, the destructive power is beyond anything our civilization has engineering language for. And then the wind encounters the mountains. This is where the atmospheric physics becomes almost artistic in its violence. When a supersonic airflow meets a mountain range, the Himalayas, the Andes, the Rockies, the Alps, it does not simply flow over it. The interaction creates atmospheric shock waves, compression waves and expansion fans, the same phenomena that fighter pilots deal with at transonic speeds, but scaled to continent-spanning mountain ranges and played out through an entire planetary atmosphere. On the eastern faces of mountain ranges, the compressed air creates regions of superheated pressure. On the western faces, expansion creates regions of catastrophic low pressure. The mountain ranges themselves, already being torn apart by the simultaneous global earthquake, are now subjected to aerodynamic forces that no rock formation is designed to resist. But we are only 60 seconds in, and the oceans have not yet caught up. The world's oceans contain approximately 1.335 billion cubic kilometers of water. Like the atmosphere, like every loose object on the surface, this water has inertia. It was rotating with the planet. Now the planet has stopped, and 1.335 billion cubic kilometers of water is still moving east. Oceanographers at institutions like the Woods Hole Oceanographic Institution in Massachusetts have studied how water behaves under extreme forcing conditions. Tsunami research, storm surge modeling, submarine landslide studies, all of these give us partial windows into the behavior of large water masses under sudden, violent forcing. What they tell us is this: the ocean does not stop when Earth stops. The ocean, like the atmosphere, continues moving east. But unlike air, water is essentially incompressible. It cannot be compressed into shock waves in the same way. Instead, it piles up against every western coastline on Earth. Picture the Atlantic Ocean, the entire body of water, 314 million square kilometers of it, with an average depth of 3,300 meters, continues moving east after the planet stops. It moves toward the coastlines of Europe and Africa. What arrives is not a wave in any conventional sense. It is the entire ocean moving as a single coherent body, impacting continental margins at hundreds of kilometers per hour. The concept closest to this in normal oceanography is a megatsunami, a tsunami generated not by a submarine earthquake, but by extreme atmospheric pressure changes. The largest megatsunamis in geological history, like the one generated by the Chicxulub asteroid impact 66 million years ago, are estimated to have produced waves hundreds of meters high that circumnavigated the globe multiple times. What we're describing would dwarf Chicxulub. On the western coasts, the Pacific coast of the Americas, the Atlantic coast of the United States, the ocean is pulling away. The water is moving east, away from these shores. Enormous regions of ocean floor are exposed as the water retreats. The continental shelves emerge from the ocean for perhaps the last time in geological history, as the water that covered them for millions of years rushes east in a single catastrophic pulse. This is the first 60 seconds. The earthquakes, the volcanic destabilization, the supersonic wind, the oceanic megatsunami, and somewhere in deep underground bunkers, in the deepest mines, in the most sheltered geological formations, a handful of humans are still alive. They have survived the first minute. What is coming next will test every instinct for survival they possess. Minutes 1 through 10, when the sky becomes a weapon. They are still alive. Somewhere beneath the shattered surface of a world that has just experienced the most violent 60 seconds in its 4.5 billion-year history, human survivors cling to existence in the darkness. Deep mine shafts in South Africa, where gold is extracted from depths of nearly 4 kilometers. Subway tunnels beneath cities that no longer exist above them. Military bunkers carved into granite mountains designed to survive nuclear strikes, now serving a purpose their engineers never imagined. These people felt the earthquake. They felt the air pressure change so violently that it ruptured eardrums and collapsed lungs. They heard sounds no human ear was designed to process. But they survived the first minute. Now comes minute 2. And minute 2 brings something that even the most prepared survivor, even the most sophisticated bunker, was not designed to handle. The atmosphere is still moving. This is the critical point that most people miss when they first think about this scenario. The atmosphere does not stop when the ground stops. It does not stop in the first 60 seconds. It does not stop in the first 10 minutes. The atmosphere is a fluid, a compressible, turbulent, chaotic fluid, and its response to the sudden stopping of its underlying surface is not a single event. It is a cascading series of events that evolve over minutes, hours, and days. Let us understand the scale of what is happening in the sky above our survivors. The troposphere, the lowest layer of the atmosphere where all weather occurs, where clouds form, where aircraft fly, extends to approximately 12 kilometers altitude at mid-latitudes. It contains roughly 80% of the atmosphere's total mass, and in the minutes following the stop event, it is a supersonic chaos unlike anything that has existed in Earth's atmosphere since the planet was young. Atmospheric scientists at the European Centre for Medium-Range Weather Forecasts in Reading, England, run some of the world's most sophisticated climate and weather models. Their systems can model atmospheric behavior at scales from individual storm cells to planetary circulation patterns. They understand, perhaps better than anyone, how interconnected atmospheric systems are, how a pressure change in the Pacific can influence rainfall in Europe weeks later. What their models tell us about supersonic atmospheric disruption is deeply unsettling. When an airflow transitions through the speed of sound, what aerodynamicists call going transonic, its behavior changes fundamentally. Below the speed of sound, pressure disturbances travel ahead of a moving object, allowing the air to prepare for what is coming. Above the speed of sound, no warning can travel ahead. The result is a shock wave, a nearly instantaneous discontinuity in pressure, temperature, and density. In minute 2 and 3 of our scenario, the atmosphere is generating shock waves not from a single moving object, but from every terrain feature on the surface of the planet simultaneously. Every hill, every mountain ridge, every coastline, every canyon wall is an obstacle in a supersonic airflow. Every one of them is generating shock waves, compression fans, turbulence cascades. The interaction of these waves with each other creates what fluid dynamicists call shock-shock interactions, events where two shock waves collide, generating pressures and temperatures far exceeding either wave alone. In the context of a planetary atmosphere undergoing this kind of forcing, these interactions happen trillions of times per second across the entire surface of the globe. The temperature implications are staggering. When air is compressed rapidly, as happens in a shock wave, its temperature rises. This is the same principle that makes a bicycle pump warm when you use it quickly, scaled up by many orders of magnitude. In the shockwave interactions occurring across Earth's atmosphere in minutes 2 through 5, air temperatures in certain zones spike by hundreds of degrees Celsius in fractions of a second. This is not a gradual warming. This is the atmosphere catching fire. Not everywhere. The physics is uneven, chaotic, violent in its variability. Some regions experience temperature spikes sufficient to ignite vegetation, melt asphalt, and vaporize standing water. Other regions, caught in the expansion fans behind shock waves, experience sudden temperature drops of equal extremity. The atmosphere is simultaneously burning and freezing, depending on which side of a shockwave boundary you happen to occupy. But there is something happening in the upper atmosphere that will have consequences far beyond the first 10 minutes. Something that most catastrophe analyses completely overlook. The ozone layer is being destroyed in real time. The stratospheric ozone layer sits between 15 and 35 kilometers altitude. It is the planetary shield that absorbs the sun's ultraviolet B and ultraviolet C radiation. Without it, the surface of Earth receives the full ultraviolet spectrum from a star that is, by cosmic standards, extremely close. Organisms that evolved under the protection of this shield have no biological mechanisms to survive prolonged, full-spectrum solar UV exposure. The ozone layer is chemically fragile. This is why chlorofluorocarbons, CFCs, the chemicals once used in refrigerators and aerosol cans, were so devastating to it. They catalyzed chemical reactions that destroyed ozone molecules faster than they could be replenished. The Antarctic ozone hole, first documented by British Antarctic Survey scientists Joseph Farman, Brian Gardner, and Jonathan Shanklin in their landmark 1985 paper in the journal Nature, showed the world how easily this shield could be compromised. In minutes 3 through 10 of our scenario, the stratosphere is subjected to conditions it has never experienced in its existence. The supersonic airflow from the lower atmosphere is driving turbulent mixing between the troposphere and stratosphere, layers that are normally kept separated by a temperature inversion called the tropopause. This mixing is injecting tropospheric air, laden with water vapor, nitrogen oxides, and the particulate debris of a shattered civilization, into the ozone layer. Simultaneously, the shock wave heating of the lower stratosphere is driving rapid chemical reactions that consume ozone directly. Nitrogen oxides, produced in enormous quantities by the lightning that is now occurring continuously across a shattered atmosphere, are among the most efficient ozone-destroying compounds known to atmospheric chemistry. Within 10 minutes of the stop event, the ozone layer is compromised globally. Not damaged, not thinned, functionally destroyed over large regions of the planet. This fact, this single atmospheric chemistry fact, changes the long-term survival calculus for every organism on Earth. But we are getting ahead of ourselves, because in minute 4, something happens on the surface that our survivors in their deep shelters will feel very clearly. The first megatsunami arrives on eastern coastlines. Let us be precise about what this means. The ocean that was rotating with the planet, moving east at hundreds of kilometers per hour, has been moving continuously since the stop event. In 4 minutes, water moving at, let us say, 1,000 kilometers per hour has traveled approximately 67 kilometers. But the wave dynamics are more complex than simple translation of water mass. As the oceanic water is displaced eastward, it piles up against continental margins in a way that oceanographers describe as inundation on a geological scale. The wave arriving at the western coasts of Europe and Africa in minute 4 is not a tsunami in the conventional sense, not a wave that rises, crashes, and recedes. It is a wall of water, potentially hundreds of meters high, backed by the momentum of an entire ocean that simply does not stop. The modeling done by researchers like Stephen Ward at the University of California, Santa Cruz, who has published extensively on tsunami dynamics and large-scale inundation scenarios, suggests that a wave of sufficient momentum does not behave like a beach wave. It behaves like a flood that keeps arriving. The water does not retreat. The pressure behind it, the weight of an entire ocean still in motion, ensures that the inundation is permanent on the timescale of hours. Continental Europe west of the Rhine, the British Isles, the Atlantic coast of Morocco and Mauritania, the western coast of Portugal and Spain, all of it submerged under hundreds of meters of water within minutes. Not eventually, not gradually, in minute 4. Meanwhile, on the other side of the world, something equally strange is happening on the western coasts. The ocean has pulled away. The Pacific has retreated from the coasts of California, Oregon, Washington, British Columbia. The Pacific has retreated from Chile, Peru, Ecuador. For the first time in human history, for perhaps the first time in geological history at this speed, the continental shelf is exposed. Survivors near the Pacific coast of North America, if any exist, would see something no human eye was meant to see: the ocean floor. Stretching outward, wet and alien and covered in the accumulated sediment of millions of years. Strange valleys and ridges, the topography of an underwater world suddenly naked under an open sky. Ancient shipwrecks, lost harbors, drowned coastlines from the last ice age when sea levels were 120 meters lower than today. This exposure would not last. The physics that pulled the ocean away will eventually reverse, but not for hours. And when it reverses, it will not be a gentle return. But minute 6 brings us back to the atmosphere, because something is happening in the sky that our physics has been building toward since the first second. The jet stream is gone. This requires some explanation, because the jet stream is one of the most important and least understood features of Earth's atmosphere. Discovered by pilots flying high-altitude bombing missions in World War II, particularly Japanese pilot Tsutomu Fujita, who would later become famous for discovering microbursts, the jet stream is a narrow band of extremely fast-moving air in the upper troposphere, typically at altitudes between 9 and 12 kilometers. The jet stream is generated by the interaction of temperature gradients between tropical and polar air masses and the Coriolis effect, the deflection of moving air caused by Earth's rotation. It moves at speeds between 100 and 400 kilometers per hour. It is the primary driver of weather systems in the mid-latitudes. It is why weather in Europe comes from the west, why storm tracks across North America follow predictable paths, why winter in Britain is milder than its latitude would suggest because of the heat carried by the Gulf Stream underneath a steering jet. When Earth stops rotating, the Coriolis effect ceases instantly. There is no longer a rotational deflection of moving air. The temperature gradients between tropical and polar regions still exist. They are driven by differential solar heating, which has nothing to do with rotation. But without the Coriolis effect to organize them into coherent circulation patterns, the atmosphere loses the structure that made it predictable. The jet stream does not slow down. It does not simply stop. It disintegrates into chaotic, fragmentary airflows that have no coherent direction, no consistent altitude, no organizing principle. The largest coherent weather system on Earth dissolves in minutes. In its place, something emerges that atmospheric scientists call direct thermal circulation. Without rotational forcing, the atmosphere begins to circulate based purely on temperature differences. Hot air rises at the equator. Cool air sinks at the poles. The result is a single, massive convection cell in each hemisphere, a direct pole-to-equator circulation that has not existed on Earth for billions of years. This circulation pattern is what Earth's atmosphere looked like before it had significant rotation. Paleoclimatologists studying ancient atmospheric conditions, using data preserved in rock formations, isotope ratios, and ancient weather patterns encoded in sedimentary layers, have reconstructed versions of this circulation from Earth's deep past, when the planet rotated much faster or slower than today. The transition to this circulation takes hours to fully establish. But in minutes 6 through 10, the chaotic intermediate state is something no meteorological system ever modeled. And then there is the lightning. In a normal atmosphere, lightning is generated by the collision of ice crystals and supercooled water droplets in cumulonimbus clouds, creating charge separation that eventually discharges as a lightning bolt. The global average is approximately 100 lightning strikes per second, around 8.6 million per day. This number, measured by NASA's Lightning Imaging Sensor on the TRMM satellite, represents the baseline electrical activity of a normal, rotating Earth atmosphere. In minutes 1 through 10 of our scenario, the atmospheric turbulence, shock wave interactions, and violent mixing of air masses at different temperatures and humidities is generating charge separation at a rate that dwarfs anything in recorded meteorological history. The atmosphere is not producing 100 lightning strikes per second. It is producing lightning continuously, not as discrete strikes, but as a near constant electrical discharge across vast regions of sky, a phenomenon sometimes called Elmo's fire in maritime tradition, but here manifested at a scale that turns the sky into a solid sheet of light. Researchers studying lightning climatology, like those at the National Severe Storms Laboratory in Norman, Oklahoma, have documented lightning super outbreaks associated with severe convective events. The largest single lightning events ever recorded, the mega flash lightning bolts documented by the World Meteorological Organization, including one measured at 768 kilometers in length over the United States in 2020, give us a sense of how energetic individual lightning events can be. What is happening in minutes 1 through 10 is not a super outbreak. It is a global electrical firestorm. Every thunderstorm that has ever existed on Earth simultaneously, multiplied by the energy input of supersonic atmospheric forcing. The electromagnetic pulse generated by this continuous lightning activity is itself a catastrophe layered onto catastrophe. Any electronic system not shielded in a Faraday cage is destroyed. Any electronic system that survived the initial physical destruction is now fried by a continuous electromagnetic assault from every direction simultaneously. In minute 8, our survivors in their deep shelters are in complete. Their electronics are dead. Their communications are severed. They cannot know what is happening on the surface. They cannot know if anyone else survived. They cannot know if the shaking has stopped. Because it has not. The global seismic event that began in second zero is still evolving. Aftershocks from the simultaneous rupture of every fault line on the planet are occurring at a rate that seismometers, if any were still functioning, could not distinguish as individual events. It is simply continuous ground motion. A planet that cannot stop trembling. And in minute 10, the survivors face their first practical crisis. Air. The ventilation systems of their shelters, whether military bunkers, mine shafts, or subway tunnels, were designed to filter and circulate air from the surface. The air on the surface is no longer breathable in many regions. It is laden with pulverized rock dust from the global seismic event, with combustion products from the fires ignited by atmospheric shock heating, with volcanic gases from the thousands of volcanoes now in various states of violent eruption. The survivors must choose: keep the ventilation running and risk pulling poisoned air into their shelters, seal the ventilation, and begin consuming their limited internal oxygen supply. It is minute 10 of 48 hours. They have 4,790 minutes remaining. And the worst is not behind them. The worst has not yet begun. Minutes 10 through 60. The oceans rise. 10 minutes into the end of the world, and the survivors have already made the most important decision of their lives. Seal the vents. Conserve the air. It is the right choice. It is also a death sentence. Delayed, not avoided. But before we descend into the shelters, we need to look up. Because in minute 11, the dust reaches the upper atmosphere. The global seismic event of the first 60 seconds pulverized rock on a continental scale. Supersonic winds atomized that material further, grinding particles down to sizes so fine they will remain suspended in the stratosphere for years. Researchers studying the Chicxulub impact of 66 million years ago, including Charles Bardeen at the National Center for Atmospheric Research, calculated that ejecta from that collision reduced sunlight reaching Earth's surface by up to 99%. What is entering the atmosphere now is not Chicxulub, but it is not trivial either. Pulverized rock, combustion aerosols, volcanic ash from thousands of simultaneously erupting volcanoes, all of it rising into the stratosphere together. By minute 15, the sky has changed color. Not the red-orange of a dusty sunset, something darker, something amber-brown that has no name in ordinary human experience, because ordinary human experience has never required one. Any shelter depending on solar power loses that resource permanently. Now the oceans demand our attention, because what is happening to them in minutes 10 through 60 is the most physically dramatic component of this entire scenario. The Atlantic Ocean contains 314 million square kilometers of water. That water was rotating with the planet. Now the planet has stopped, and the ocean has not. It is moving east, toward Europe, toward Africa, as a coherent mass. When a moving water mass encounters a shoaling continental shelf, it slows, compresses, and rises. This is standard tsunami physics. The shoaling effect amplifies wave height dramatically as ocean depth decreases. Researchers including Stephen Grilli at the University of Rhode Island, who has modeled large-scale ocean inundation events, give us the framework for what follows. Minute 20. The oceanic displacement reaches the European continental shelf. Britain, gone. Ireland, submerged. Portugal, western Spain, Morocco. All of it underwater that does not recede, because the ocean behind it is. Paris sits 35 meters above sea level. Under normal tsunami conditions, Paris is safe from any conceivable ocean event. Under our scenario, the English Channel, narrowing from 250 kilometers wide to 34 kilometers at Dover, funnels the incoming water into a jet of extraordinary height and velocity. The flat Netherlands, northern Germany, the Danish peninsula, essentially at sea level, offer no resistance. Amsterdam, Hamburg, Copenhagen, minute 30. They no longer exist as surface features. On the other side of the world, the Pacific tells a different story. The ocean has retreated from the Western Americas. The continental shelf, normally covered by 50 to 200 meters of water, is exposed. An alien landscape of deep sediment, hydrothermal vent communities, ancient drowned coastlines from the last ice age. The smell of hydrogen sulfide and methane from destabilized seafloor sediment would be detectable hundreds of kilometers inland. But that water has not disappeared. It has piled against Japan, the Philippines, Indonesia, Eastern Australia. Japan, a nation intimately familiar with tsunamis, where the 2011 Tohoku disaster generated waves 40 meters high, now faces inundation that dwarfs anything in its recorded history. Minute 30 also brings the survivors a new crisis, one that has nothing to do with wind or water. Heat. Earth's geothermal gradient increases approximately 25 to 30 degrees Celsius per kilometer of depth in stable crust. In geologically active areas, far more. The simultaneous rupture of every fault on Earth is releasing accumulated stress energy as heat. Magma that was contained in volcanic systems is now moving upward through newly created fractures. In deep South African gold mines, descending nearly 4 kilometers, where ambient rock temperature already reaches 60 degrees Celsius, the refrigeration systems that make work possible have been dead since minute 1. Without power, the temperature climbs toward ambient, 60 degrees Celsius, the threshold beyond which human survival becomes impossible. The survivors feel it in minute 30 as a subtle warmth in the walls around them. By minute 45, it is no longer subtle. Above them, something is happening that they cannot detect, but that will determine the long-term fate of everything alive. The magnetic field is beginning to change. Earth's magnetosphere is generated by convection of liquid iron in the outer core, the geodynamo. The outer core, separated from the mantle by the core-mantle boundary, does not stop instantly when the crust stops. It has its own inertia. But the organized convection patterns that produce a stable dipolar magnetic field depend partly on rotational forcing from the mantle above. Remove that forcing abruptly, and the convection begins to reorganize. The magnetic field does not fail in the first hour, but it begins to wobble. To lose the organized structure that makes it an effective planetary shield against solar wind, the continuous stream of charged particles from the sun that, without deflection, strips atmospheric molecules from exposed planets. Mars lost its magnetic field billions of years ago. Its atmosphere followed. Minute 60. 1 hour since Earth stopped spinning. The survivors are in darkness. Oxygen is measurably depleted. The walls are warm and getting warmer. The ground is still moving because the simultaneous rupture of every fault on Earth generated aftershock sequences that are now cascading and interfering with each other globally, with no natural endpoint in the near term. Above them, the atmosphere is poisonous. The oceans have permanently reshaped every coastline on Earth. The ozone layer is compromised. The magnetic field is reorganizing. They have survived 60 minutes. They need 47 more hours. And in the next hour, something happens that none of them expected. Something that, against all logic, might actually help them survive. Hours 1 through 6, the unexpected factor. 1 hour in, the world above is unrecognizable. But something is changing in the atmosphere that no disaster model fully anticipated. Something that emerges not despite the chaos, but because of it. The supersonic winds are slowing down. Not stopping, not calming into anything resembling normal weather, but the initial kinetic energy of the atmosphere, that enormous eastward momentum from the stop event, is being converted. Converted into heat, into turbulence, into the violent reorganization of atmospheric circulation. And as that energy dissipates, the wind velocities at the surface begin to drop, from supersonic to merely catastrophic. By hour 2, surface winds in mid-latitudes have decreased from thousands of kilometers per hour to somewhere between 200 and 500 kilometers per hour. Still incompatible with surface survival, still capable of moving vehicles, stripping soil, driving debris through rock faces, but no longer the planetary sandblaster of the first 60 minutes. This matters for one specific reason. The shelters can breathe again. Not safely, not cleanly. The air outside is still laden with rock dust, volcanic gases, combustion products. But the pressure differential that was making any surface ventilation impossible, the supersonic airflow that would have torn ventilation systems apart, has eased sufficiently that filtered air exchange becomes theoretically possible. The survivors who understood atmospheric physics, who waited out the first hour before attempting any ventilation, now have an option. A dangerous option, but an option. Here is what they cannot know, sealed in their shelter. Here is what is happening on the surface above them. The fires. In the first hour, atmospheric shock heating ignited surface fires across vast regions of the planet. Forests, grasslands, the remains of cities, all of it burning simultaneously. Under normal conditions, large fires create their own weather systems. The heat generates updrafts, which pull in surrounding air, which feeds the fire, which generates more heat. Firestorms. The same phenomenon observed in Hamburg and Dresden during World War II bombing campaigns, where conventional fires merged into self-sustaining atmospheric convection systems with winds at their bases exceeding 150 kilometers per hour. What is burning now is not a city, it is a continent. Researchers studying paleofire events Ancient global fire episodes recorded in charcoal layers in geological sediments have documented episodes where large fractions of Earth's terrestrial vegetation burned within geologically short timeframes. The end Cretaceous boundary, the same layer that records the Chicxulub impact, contains a globally distributed charcoal layer indicating widespread fires. Scientists, including Wendy Wolbach at DePaul University, have published research in journals including Earth and Planetary Science Letters documenting this soot layer and its implications for post-impact darkness and cooling. What is happening now is a fire event of comparable scale, not caused by an asteroid, but by atmospheric physics. And like the Chicxulub fires, it is loading the atmosphere with soot and combustion products that will have consequences far beyond the fires themselves. By hour 3, a feedback loop is establishing itself. The fires are consuming oxygen. The fires are producing carbon dioxide and carbon monoxide. The fires are injecting enormous quantities of black carbon, soot, into the atmosphere, where it absorbs solar radiation and heats the upper atmosphere while simultaneously blocking sunlight from reaching the surface. This is the beginning of what climate scientists call a nuclear winter scenario, though in this case caused not by nuclear weapons, but by the combined effect of impact dust, volcanic ash, and fire soot. Research by Alan Robach at Rutgers University and Brian Toon at the University of Colorado Boulder, published in journals including the Journal of Geophysical Research, has modeled how soot injected into the stratosphere from large-scale fires remains aloft for years, dramatically reducing surface temperatures. For the survivors underground, this feedback loop is paradoxically helpful in one specific way. The surface is getting darker, and darker means cooler. And cooler means the geothermal heat building in their shelters from below is partially offset by a reduction in surface heat from above. It is not salvation. It is merely a slight reduction in the rate of their slow cooking. Hour 4 brings a geological development that no shelter was designed to handle: the volcanoes. We established in the first minutes that every major volcanic system on Earth was destabilized by the global seismic event. Now, 4 hours later, those systems have had time to respond. Magma that was sitting in shallow chambers under pressure, held in equilibrium by surrounding rock, now fractured by the seismic event, has been moving upward through new pathways. The result is not a series of individual volcanic eruptions. It is a global volcanic event. Volcanologists classify eruptions using the Volcanic Explosivity Index, or VEI, a logarithmic scale where each integer increase represents a 10-fold increase in erupted volume. The 1980 Mount St. Helens eruption was VEI 5. The 1815 Tambora eruption, the largest in recorded human history, which caused the year without a summer in 1816, was VEI 7. The supervolcano eruptions preserved in the geological record, like the Toba eruption of approximately 74,000 years ago, reached VEI 8. What is occurring in hour 4 is not one Tambora. It is hundreds of them, simultaneously. The Toba eruption is particularly relevant here. Genetic studies of human populations, combined with geological dating of the Toba ash layer found across South Asia, Southeast Asia, and East Africa, led some researchers, including Stanley Ambrose at the University of Illinois, to propose a genetic bottleneck hypothesis, that the Toba eruption was so catastrophic that it reduced the global human population to perhaps 10,000 individuals. This hypothesis remains debated, but the climatic effects of Toba, a volcanic winter estimated to have lasted 6 to 10 years, reducing global temperatures by 3 to 5 degrees Celsius, are well documented in ice cores from Greenland and Antarctic. Hour 4 of our scenario produces atmospheric sulfur dioxide loading from simultaneous volcanic activity that dwarfs Toba. Sulfur dioxide injected into the stratosphere reacts with water vapor to form sulfuric acid aerosols, tiny droplets that reflect incoming sunlight back into space, cooling the surface. It is the same mechanism that caused cooling after Pinatubo in 1991, which reduced global temperatures by approximately half a degree Celsius for 2 years from a single eruption. The cooling from simultaneous global volcanism in hour 4 is not half a degree. The models suggest something between 15 and 30 degrees of surface cooling, beginning within days and persisting for years. For the survivors, this is deeply contradictory news. The volcanic winter will eventually make the surface cooler, potentially survivable in terms of. But the volcanic gases, sulfur dioxide, hydrogen sulfide, carbon dioxide, hydrogen fluoride, make the surface atmosphere chemically lethal for timescales far beyond the physical destruction. Hour 5. And now we must address something that has been building since the first minute. The oceans have been moving, crashing into coastlines, reshaping continental margins. But water, unlike air, is nearly incompressible, and the energy it carries must go somewhere. Where the oceanic displacement events have crashed into continental margins and mountain ranges, that energy is being reflected, scattered, converted into complex wave patterns that are now propagating back across the ocean basins. Oceanographers call these reflected waves seiches when they occur in enclosed basins, the resonant sloshing of water trapped in a lake or bay. In the open ocean, the equivalent phenomenon is a complex interference pattern of waves traveling in multiple directions simultaneously. By hour 5, every ocean basin on Earth is a chaotic superposition of waves. The initial displacement event, its reflections from continental margins, secondary waves generated by submarine landslides triggered by the seismic event, waves from tsunamis generated by volcanic collapses of island volcanoes. The surface of every ocean looks nothing like water as we know it. It looks like the inside of a washing machine. For any coastal survivor who somehow reached high ground, the peaks of the Scottish Highlands, the Swiss Alps, the Ethiopian Plateau, the ocean visible from that high ground is not a stable surface. It is a churning, spray-filled chaos of intersecting wave trains, moving in every direction, white with foam and brown with suspended sediment. Hour 6. And in the shelters, the survivors face their most complex decision yet. The oxygen situation is becoming critical in smaller shelters. The heat is manageable, but rising. The ventilation filters, designed for industrial dust and chemical contaminants, are struggling with an atmosphere that contains compounds they were never tested against. Some filters are failing. But the seismic activity has decreased measurably in the past 2 hours. From the continuous vibration of the first hour, the ground motion has settled into something that, while still far exceeding any normal aftershock sequence, has discrete events separated by moments of relative stillness. The survivors who are geologists, who are mining engineers, who understand rock mechanics, are reading the walls of their shelters the way doctors read vital signs. The pattern of cracking, the temperature gradient, the sound of rock under stress. Some of them are making a calculation. Not to the surface. The surface is still death. But upward, toward intermediate depths, toward levels where the air might be filtered enough to breathe, where the temperature is lower than the deep, hot rock, where the structural damage from the seismic event might have created new pathways, or sealed old ones dangerously. It is the most dangerous kind of decision, made on incomplete information, under time pressure, with irreversible consequences. 6 hours since Earth stopped spinning. The planet has a new face. The coastlines of every continent have been redrawn. The atmosphere is a toxic, darkening shroud. The volcanic winter has begun. The magnetic field continues its slow reorganization, and somewhere in the darkness, humans are still alive, deciding whether to move. Hours 6 through 24. The first day ends. 6 hours in. The world has stopped spinning, but has not stopped changing. In fact, in some ways, the most profound transformations are only beginning. Let us start with the sky. Because by hour 6, the sky above Earth is doing something that no human eye has ever witnessed in the entire history of our species. It is standing still. Not metaphorically, literally. The sun, which for 4.5 billion years has risen in the east and set in the west, driven by Earth's rotation, is no longer moving across the sky. It hangs, fixed, at whatever position it occupied at the moment of the stop event. If you were on the daylight side of Earth at 0 hour, the sun is still there, in the same position, unmoving, a fixed point of light in a darkening, debris-choked sky. If you were on the night side, you are still in darkness. The stars above, filtered through the thickening atmospheric haze, are stationary. No rotation, no progression. The sky is a photograph. This single fact, the cessation of the apparent motion of the sun, has implications that cascade through every system on Earth. Consider temperature. In a normal rotating Earth, solar energy is distributed across the surface through the cycle of day and night. The daylight hemisphere absorbs solar radiation. The night hemisphere radiates heat back into space. The rotation ensures that no single point on the surface is continuously heated or continuously cooled. It is a planetary heat distribution mechanism of elegant efficiency. Remove the rotation, and this mechanism fails completely. The daylight hemisphere, the half of Earth facing the sun at the moment of the stop, begins to accumulate heat with nothing to interrupt it. The night hemisphere, the half facing away, begins to radiate heat into space with nothing to interrupt that either. This is not a gradual process. The temperature differential between the day side and night side of Earth begins to grow from the first hour, and by hour 12, it is already larger than anything in recorded climate history. Atmospheric scientists modeling tidally locked planets, worlds that orbit so close to their stars that gravitational forces have stopped their rotation, leaving one face permanently toward the star and one face permanently away, have studied exactly this phenomenon. Research published in journals including Astrophysical Journal Letters by scientists including Jérémy Lecomte at the Laboratoire d'Astrophysique de Bordeaux has modeled the atmospheric dynamics of tidally locked terrestrial planets. Their models show something counterintuitive. The atmosphere does not simply allow the day side to boil and the night side to freeze. The temperature differential itself drives atmospheric circulation. Hot air rising on the day side, flowing toward the night side at high altitude, cooling, descending, and returning at low altitude. A single planet-spanning convection cell in each hemisphere, driven purely by the temperature difference between day and night. This is the new atmospheric circulation we mentioned in Chapter 5. By hour 12, it is establishing itself as the dominant pattern. The chaotic, supersonic winds of the first hours are giving way to something more organized, but no less dangerous. The day-to-night atmospheric flow at high altitudes reaches speeds of several hundred kilometers per hour. Not supersonic, not the planetary sandblaster of the first hour, but sustained, directional, and carrying with it the heat, the volcanic ash, the combustion products of the burning day side toward the cooling night side. At the terminator, the boundary between the permanent day side and the permanent night side, the collision of hot day side air with cold night side air creates a permanent weather system unlike anything in Earth's history. A continuous wall of storms stretching around the entire circumference of the planet, where air masses of radically different temperatures and humidities collide permanently. Researchers who study the atmospheres of tidally locked exoplanets call this feature the terminator jet, a high-velocity wind band that circles the planet at the day-night boundary. On Earth, in our scenario, this feature is not a theoretical construct in a distant solar system. It is a ring of permanent, violent weather circling the planet, visible from space as a continuous band of cloud and lightning stretching from pole to pole. Hour 8. And on the day side, the temperature is climbing. The equatorial day side, the region of Earth facing most directly toward the Sun at the moment of the stop, is receiving approximately 1,361 watts of solar energy per square meter, continuously, without the interruption of night, without the moderating effect of rotation distributing that energy around the globe. Under normal conditions, Earth's surface reaches thermal equilibrium through a balance of incoming solar radiation and outgoing infrared radiation. The equilibrium temperature depends on surface albedo, how reflective the surface is, and the greenhouse effect of the atmosphere. The global average surface temperature of around 15 degrees Celsius represents this equilibrium under normal rotating conditions. Without rotation, the day side cannot reach equilibrium. The incoming solar energy exceeds the outgoing infrared radiation, and the surface temperature climbs continuously. By hour 12, exposed rock surfaces on the equatorial day side are reaching temperatures of 80 to 100 degrees Celsius in the absence of atmospheric cooling. The atmospheric circulation is providing some cooling. The day-to-night airflow carries heat away, but not enough to prevent a runaway heating trend in the most exposed regions. Water boils at 100 degrees Celsius at sea level. By hour 20, standing water on the equatorial day side is beginning to evaporate at rates that have no parallel in Earth's climate history. The oceans on the day side are not boiling. The thermal mass of the ocean is enormous, and it will take far longer than 48 hours to raise ocean temperatures significantly. But surface evaporation is proceeding at extraordinary rates, loading the already disrupted atmosphere with water vapor. Water vapor is the most powerful greenhouse gas in Earth's atmosphere, more powerful than carbon dioxide, more powerful than methane. The addition of enormous quantities of water vapor to an already disrupted atmospheric system accelerates the day-side heating further. On the night side, the opposite process is accelerating. Without incoming solar radiation, the night side is radiating its stored heat into space. The rate of cooling depends on the atmospheric greenhouse effect. The same water vapor and carbon dioxide that trap heat on the day side also trap heat on the night side, slowing the cooling. But the net effect is still strongly negative. By hour 12, night-side surface temperatures at mid-latitudes are dropping below 0 degrees Celsius. By hour 24, they are approaching -40 in continental interior regions. The night side is freezing, not gradually, in the way that winter brings frost over weeks and months, rapidly, in the way that a refrigerator cools, because the night side of Earth has essentially become a radiator pointed at the cold of space, with no solar input to compensate. Bodies of water on the night side begin freezing from the surface down. Not the deep oceans, their thermal mass is too great, but lakes, rivers, shallow coastal waters. By hour 24, the night side of Earth looks, from space, like a planet entering an ice age in fast forward. And between the burning day side and the freezing night side, at the terminator, the permanent storm wall rages. Hour 10. And in the shelters, the survivors are making their move. The decision to ascend, to move from deep shelter toward intermediate levels, is being executed by the most organized survivor groups. Mining operations, with their established protocols for underground navigation and their stockpiles of breathing equipment, are best positioned. Military bunkers, designed with multiple compartmentalized levels, give their occupants options. What the ascending survivors find in the intermediate levels tells them, for the first time, something about what has happened above. The air pressure has changed. Normal atmospheric pressure at sea level is 101,325 pascals, one standard atmosphere. In the first hours of our scenario, the atmospheric dynamics we described, the supersonic winds, the pressure waves, the shock interactions, created enormous local variations in surface pressure. Some regions experienced pressure drops equivalent to being at altitude. Others experienced pressure spikes. By hour 10, as the new atmospheric circulation is establishing itself, surface pressure is beginning to stabilize. But it is not stabilizing at normal values. The redistribution of atmospheric mass, from the churning, turbulent chaos of the first hours toward the organized day-to-night flow, has changed the pressure distribution across the surface. At the terminator, the convergence of day-side and night-side air masses creates a permanent high-pressure zone, air piling up where the two circulation cells meet. On the deep day side and deep night side, the diverging airflows create lower pressure regions. The survivors ascending in their shelters notice this as a change in the feel of the air at different levels. Subtle, but measurable to people trained to read underground environments. Hour 12, halfway through the first day. The geological activity is evolving. The continuous seismicity of the first hours has not stopped, but it has organized itself into something with more structure. The largest fault systems, those that released the most energy in the initial stop event, are entering a phase of reduced activity. Their stress has been Smaller fault systems, loaded by stress transfer from the larger ruptures, are now the primary sources of seismic activity. The volcanic eruptions, meanwhile, are intensifying. The destabilization of magmatic systems that began in the first second is now fully expressed. Every major volcanic arc on Earth, the Pacific Ring of Fire, the Mediterranean volcanic belt, the East African Rift, is in eruption simultaneously. The scale of eruption varies. Some systems are producing relatively effusive lava flows. Others are generating explosive eruptions, of the kind that send material into the stratosphere. The cumulative atmospheric loading from these simultaneous eruptions is staggering. Volcanologists studying the large igneous provinces of the geological past, vast outpourings of volcanic material that occurred over millions of years and are associated with mass extinction events, have calculated the atmospheric sulfur dioxide and carbon dioxide emissions from these events. The Deccan Traps eruptions of approximately 66 million years ago, coinciding with the end Cretaceous mass extinction, produced an estimated 500,000 cubic kilometers of lava over roughly 30,000 years. What is erupting now is producing comparable volumes of gas in hours. The stratospheric sulfate aerosol loading from this volcanic activity is beginning to have measurable effects on solar transmission by hour 12. The sun, already fixed and unmoving in the sky, is dimming. Not from clouds, from the stratospheric veil of sulfuric acid droplets spreading from eruption sites across the globe. Hour 16. And something unexpected happens in the shelters. Contact. Not radio contact. The electromagnetic environment is still too disrupted for conventional radio communication across long distances. But low-frequency signals traveling through rock, the same principle used in through-Earth communications systems developed for mining operations, are being detected by the most sophisticated underground facilities. Other survivors, in other shelters, in other mines. They cannot exchange much information. The bandwidth of through-rock communication is extremely limited, but the signal itself, the simple fact of its existence, carries the most important message possible. Others survived the first 16 hours. The psychological significance of this cannot be overstated. The survivors who have been in isolation since 0 hour, with no information about the outside world, no confirmation that anyone else is alive, have been operating under the assumption that they might be the last humans on Earth. The confirmation that they are not, even without specific information about where, how many, in what condition, changes the calculus of survival fundamentally. People survive longer when they believe survival has a purpose. Hour 20. The day side of Earth, in its most exposed equatorial regions, is approaching conditions that make survival impossible without deep shelter. Surface temperatures in direct sun are exceeding 100 degrees Celsius. The air is a mixture of volcanic gases, combustion products, and superheated water vapor. The ultraviolet radiation penetrating the compromised ozone layer is at lethal levels for biological tissue. But in the deeper ocean, away from the immediate surface, conditions are different. The thermal mass of the ocean is moderating the temperature change. Hydrothermal vent communities, which exist in complete darkness at temperatures up to 400 degrees Celsius, are entirely unaffected by events at the surface. Life in the deep ocean, the most abundant biosphere on Earth by volume, continues largely unchanged. This is a critical scientific. The deep ocean biosphere, sustained not by sunlight, but by chemical energy from hydrothermal vents, has survived every mass extinction in Earth's history. It survived Chicxulub. It survived the Great Oxidation Event 2.4 billion years ago, which killed most of the anaerobic life then dominant on Earth. It will survive this. Life will continue on Earth after the stop event. The question is, which life? and in what form? Hour 24. The first day ends. Except, of course, there is no first day ending. The sun has not moved. There is no sunset on the day side. There is no sunrise on the night side. The concept of a day, so fundamental to human biology, to circadian rhythms, to the organization of time itself, has ceased to exist. The survivors mark the passage of 24 hours by their watches, by the clocks in their shelters, by the biological rhythms of hunger and fatigue that have governed human life for 200,000 years. 24 hours. They have survived. The surface above them is unrecognizable as Earth, but they are alive. And in the next 24 hours, in the second half of our 48-hour window, the question shifts. It is no longer whether the immediate physical catastrophe will kill them. It is whether the world that emerges from this catastrophe is one that any of them can survive long enough to see. Hours 24 through 48, the second day. 24 hours. The survivors have lived through something that has no name in human experience. No mythology prepared them for it. No religion predicted it in these terms. No science fiction writer imagined it with sufficient precision. And now they face the second day. Except the second day is identical to the first in one fundamental sense. The sun has not moved. The terminator has not shifted. The burning day side is still burning. The freezing night side is still freezing. This is the new reality. Not a temporary crisis with a resolution, a permanent state. Let us assess what exists at the 24-hour mark. The atmosphere has largely completed its transition from chaotic supersonic disruption to the new organized circulation. The day-to-night flow is established. Surface winds, while still extreme by any pre-event standard, are no longer supersonic at most locations. The terminator storm wall is a permanent feature, a continuous band of violent weather circling the planet, but predictable in its location. The volcanic eruptions continue. They will continue for months, possibly years. The simultaneous destabilization of every major magmatic system on Earth is not a brief event. Volcanoes that are awakened do not return to sleep in 48 hours. The atmospheric loading from these eruptions is cumulative, and by hour 24, the stratospheric aerosol veil is measurably reducing solar transmission, even on the day side. The day side is still receiving sunlight, but less of it than yesterday, if yesterday is even a meaningful concept anymore. Hour 26. And the survivors, attempting to ascend through their shelters, are encountering the surface for the first time. Not the open surface, the near surface, the uppermost levels of mines, the upper floors of deep bunkers, spaces that are technically underground, but close enough to the outside that the air coming through damaged sections is detectable. What they smell first is sulfur, the sharp, choking tang of hydrogen sulfide and sulfur dioxide from the volcanic activity. It is the smell of the Earth's interior, of processes that have been happening deep underground since the planet formed, now expressed at the surface on a scale never before experienced in human history. What they see, if they have any light source and any intact viewing point, is a sky that is wrong in ways that are difficult to process. The color is not blue. It is a deep brownish orange in some directions, transitioning to an almost luminescent yellow-white in the direction of the fixed sun. The clouds, the remnants of what were weather systems, are not moving in the familiar patterns of a rotating Earth. They are flowing in a single direction, from dayside to nightside, driven by the new thermal circulation. The clouds at the terminator are something else entirely. Towering cumulonimbus formations, their tops reaching into the stratosphere, permanently anchored at the day-night boundary, continuously fed by the collision of warm, moist dayside air with cold, dry nightside air. From a distance, they would look like a wall, a white and gray wall of cloud stretching from horizon to horizon, from ground to the edge of the visible atmosphere. Lightning in that wall is continuous, not individual strikes, a permanent flickering that illuminates the cloud mass from within, visible from hundreds of kilometers away on both sides of the terminator. Hour 28. The temperature divergence between dayside and nightside is accelerating. On the equatorial dayside, surface temperatures in exposed areas have exceeded 120 degrees Celsius. Water boils. Organic material that survived the initial event, tree trunks, soil organic matter, the structural components of destroyed buildings, is now pyrolyzing, charring, converting to carbon in the sustained heat. On the equatorial night side, surface temperatures have dropped to -60 degrees Celsius in continental interiors. The remaining moisture in the air is freezing out, falling as snow on a surface that has never experienced these temperatures in recorded history. The Sahara, if it is on the night side at the moment of the stop event, is buried under snow. The temperate zones, the mid-latitudes between the equatorial extremes and the poles, are experiencing intermediate conditions. Dayside temperate zones are hot, hazy, sulfurous, but not immediately lethal in terms of temperature. Nightside temperate zones are cold and getting colder, but not yet at the extremes of the equatorial night. These temperate zones represent the best near-term survival environments on the surface, if any surface survival is possible at all. Hour 30. And in the oceans, the dynamics are entering a new phase. The initial oceanic displacement event, the catastrophic eastward movement of ocean water that destroyed the Atlantic coasts of Europe and Africa, has largely dissipated its kinetic energy in the first 12 hours. The wave reflections, the sloshing, the chaotic interference patterns we described earlier are settling toward a new equilibrium. But it is not the old equilibrium. The oceans are not returning to their pre-event positions. Without Earth's rotation, the Coriolis effect that organized ocean currents, the Gulf Stream, the Kuroshio Current, the Antarctic Circumpolar Current, no longer operates. The great conveyor belt of ocean circulation, the thermohaline circulation that has regulated global climate for millions of years, is disintegrating. In its place, a simpler circulation is establishing itself. Driven purely by temperature, hot water on the day side, cold water on the night side, with a flow pattern that moves surface water from day to night and returns deep water from night to day. The same direct thermal circulation that is reorganizing the atmosphere is reorganizing the oceans. This new ocean circulation is slower than the old one. The thermohaline circulation moved enormous volumes of water at speeds of centimeters per second, but it was continuous and global. The new thermally driven circulation is similarly global but less organized, less efficient at distributing heat. The implications for the deep ocean biosphere are the hydrothermal vent communities we mentioned, the organisms that survive on chemical energy rather than sunlight, are unaffected. But the organisms that depend on the upwelling of cold, nutrient-rich deep water to support surface productivity, the phytoplankton, the zooplankton, the entire oceanic food web built on photosynthesis, are in crisis. Not immediately. Phytoplankton can survive days without light. Zooplankton can survive weeks without food. The oceanic food web has buffering capacity built up over billions of years of evolutionary history. But weeks, not months. Hour 36. 36 hours since the stop event. The survivors in the deepest shelters are facing a convergence of crises. Oxygen depletion, manageable in the first 24 hours with careful rationing, is now becoming acute in the smaller facilities. The heat from below, the geothermal warming we described in Chapter 4, has risen measurably. Rock walls that were cool at hour 0 are now noticeably warm at hour 36. The survivors who moved to intermediate levels earlier are faring better in terms of heat, but they are exposed to more atmospheric contamination. The filters that protect them from volcanic gases and rock dust are reaching their design limits. Some have already failed. The organized survivor groups, those with the clearest command structure, the most rational allocation of resources, the best technical knowledge, are making the calculation that all disaster survivors eventually must make. When do we move? And where? The answer, for those near the terminator zone, is potentially now and there. The terminator, the permanent day-night boundary, is not a comfortable place. It is a zone of continuous violent weather, of the towering storm wall we described. But its temperature is intermediate. Neither the lethal heat of the deep day side nor the lethal cold of the deep night side. It is where the new atmospheric circulation is most active, which means it is where the air exchange is greatest, which means that, over time, it may be where the volcanic gases are most diluted by atmospheric mixing. It is also, crucially, where liquid water exists on the surface. The day side is too hot for surface liquid water in its most exposed regions. The night side is freezing. But at the terminator, temperatures are in the range where water remains liquid, and where the continuous precipitation from the terminator storm wall provides a permanent water source. Researchers who study habitability on tidally locked exoplanets have identified the terminator zone as the most likely location for life on such worlds. A paper published in the journal Astrobiology by researchers including Jun Yang at Peking University modeled the climate of tidally locked Earth-like planets and found that the terminator zone maintained habitable temperatures even when the day side was too hot and the night side was too cold. We are living, in our scenario, inside that model. The terminator is where humanity survives, if humanity survives. Hour 40. And something happens that the survivors in their shelters can detect even without instruments. The seismic activity drops. Not to zero, not to normal background levels, but from the continuous, overlapping aftershock sequences of the first 24 hours to something that has recognizable, discrete events separated by genuine quiet. The largest fault systems have discharged their accumulated stress. The stress transfer cascades are running out of energy as they propagate into smaller and smaller fault systems. The global seismic crisis is not over, but it has passed its peak. The ground is still. For the first time in 40 hours, the ground is still. The psychological impact of this on the survivors is the vibration they have lived with since 0 hour, so constant that they stopped consciously registering it, the way city dwellers stop hearing traffic, is gone. The silence of a stable Earth feels, paradoxically, more alarming than the continuous motion did, because the mind knows that silence is not normal either. Hour 42. And now we must address the question that has been implicit throughout this entire investigation: the magnetic field. We established in Chapter 4 that the geodynamo, the generator of Earth's magnetic field, does not fail immediately when the crust stops rotating. The liquid outer core has its own inertia, but by hour 42, the reorganization of convection patterns in the outer core, driven by the removal of rotational forcing from the mantle above, is measurable. The magnetic field is weakening. Not catastrophically. Not yet. The timescale for significant geodynamo reorganization is thousands of years, even under normal conditions. A pole reversal, where the north and south magnetic poles swap, takes between 1,000 and 10,000 years to complete, based on paleomagnetic evidence preserved in volcanic rocks dated by researchers including Brad Singer at the University of Wisconsin-Madison. But the field is changing faster than it would under normal conditions. The organized dipolar structure, the simple north-south field that compasses point to, that deflects solar wind around the planet, is showing signs of the kind of complexity that precedes a reversal. Multiple magnetic poles appearing at different locations, the field strength decreasing at an accelerating rate. The practical implication is still in the future. The magnetosphere is still present. Solar wind is still being deflected, but the protective envelope around the planet is thinning at a rate that, if extrapolated, suggests meaningful reduction in protection within years rather than. For the survivors facing immediate crises of oxygen and heat and volcanic gases, this is an academic concern. They will not live to see the magnetic field fail if they cannot solve the problems of the next few hours. But for the long-term future of life on Earth, for whatever survives the next decade, century, millennium, the weakening magnetic field is perhaps the most significant long-term consequence of the stop event. Hour 46. 2 hours from the end of our 48-hour window. Let us take stock of what exists. The surface of Earth has been permanently altered. Every coastline on the planet has changed. The Atlantic coast of Europe and Africa has been submerged under hundreds of meters of water. The Pacific coast of the Americas has been exposed and then re-inundated in a different pattern. The topography of every continental margin has been reshaped by the combined forces of seismic activity, oceanic displacement, and volcanic construction and destruction. The atmosphere is a different chemical mixture than it was 48 hours ago. Higher in carbon dioxide from volcanic outgassing and combustion. Higher in sulfur dioxide and hydrogen sulfide from volcanic activity. Lower in ozone from the chemical destruction of the stratospheric ozone layer. The aerosol loading from volcanic sulfate, from combustion soot, from pulverized rock dust, is producing a measurable dimming of sunlight even on the permanently illuminated day side. The biosphere is in crisis everywhere except the deep ocean. Terrestrial ecosystems on the day side are being destroyed by heat, ultraviolet radiation, and chemical pollution. Terrestrial ecosystems on the night side are being destroyed by freezing temperatures and darkness. The terminator zone, where conditions are most moderate, is the only region where surface life has any near-term future. The oceans, with their enormous thermal and biological inertia, are buffering the worst effects of the stop event for marine life. But the disruption of the thermohaline circulation, the chemical changes from volcanic outgassing, and the altered light environment are beginning to stress marine ecosystems in ways that will compound over months and years. And somewhere in the darkness of shelters that are running out of oxygen and patience and light, humans are still alive. How many? Impossible to say with precision. The scenario involves too many variables, too many location-specific factors, too many individual decisions made under extreme stress. But the physics does not exclude survival. Deep shelters at high latitudes, on the dayside temperate zones where temperatures are elevated but not lethal, with adequate supplies and filtered ventilation, these are not impossible environments to survive in. The survivors who understood what was happening, who made the right decisions at each branch point, may have a path forward. Hour 48. 2 full days since Earth stopped spinning. The immediate catastrophe, the supersonic winds, the oceanic displacement, the global seismic event, the first volcanic paroxysms, is over. What remains is not recovery. There is no recovery to the pre-event state. Earth without rotation is a fundamentally different planet than Earth with rotation, and the differences are permanent. What remains is adaptation. The same process that has driven life on Earth for 4 billion years. The same process that survived Chicxulub, survived the Great Oxidation Event, survived the snowball Earth glaciations of 700 million years ago. Life adapts, or it does not. And the line between those outcomes is drawn not in geology or atmospheric chemistry, but in the decisions made by organisms, including human organisms, in the critical hours and days of a transition between one world and another. What comes after the new 48 hours? We have walked through the physics, the atmospheric mechanics, the oceanic dynamics, the geological consequences. We have followed the survivors through their darkest hours, in shelters that are running out of air and light and certainty. Now we need to step back, to look at the larger picture, to ask the question that every scientist working on this scenario eventually confronts. What does Earth look like in 1 year? In 100 years? In 1,000? Because here is the thing that makes this scenario genuinely extraordinary from a scientific standpoint. Earth without rotation is not a dead planet. It is a different planet. And the differences, while catastrophic for the civilization that existed before, create conditions that are, in the long sweep of geological time, not incompatible with life. Let us build the picture carefully. The first and most fundamental change is the day-night structure. A non-rotating Earth, locked in its orbit around the Sun, presents one face permanently toward the Sun and one face permanently away. But here is a subtlety that most treatments of this scenario miss entirely. Earth is not tidally locked to the Sun in our scenario. We posited only that Earth stopped rotating. A tidally locked planet has its rotation synchronized with its orbital period. It rotates once per orbit, so the same face always points toward the central body. Earth's orbital period around the Sun is 365.25 days. A stopped Earth, in contrast, does not rotate at all relative to the stars, but it still orbits the Sun. This means that over the course of 1 year, every point on Earth's surface will have passed through all positions relative to the Sun. The day-night boundary will have swept slowly around the planet, completing one full cycle in 1 year. This is a crucial. It means that the permanent day side and permanent night side we described in the first 48 hours are not actually permanent. They are very slowly changing. The Sun moves across the sky, not in 24 hours as it does now, but in 365 days. Each day lasts 6 months. Each night lasts 6 months. This is closer to the experience of Earth's poles, where the Sun stays above the horizon for 6 months and below it for 6 months, than to the experience of a truly tidally locked world. The implications for survival are significant. No region of Earth is permanently in darkness. No region is permanently in light. Every part of the planet experiences both, just on a timescale of months rather than hours. The temperature extremes we described, day-side surfaces exceeding 100 degrees, night-side surfaces reaching -60, are the initial extremes, before the atmosphere has time to distribute heat globally. Over weeks and months, the new atmospheric circulation spreads heat from the hot regions toward the cold regions, moderating the extremes. Researchers modeling slowly rotating planets, not tidally locked, but with rotation periods of days or weeks rather than hours, have found that the atmospheric heat distribution becomes more efficient as the rotation period increases. A planet rotating once per year, as our stopped Earth effectively does, has an atmosphere that is extremely efficient at moving heat from the warm side to the cold side. The result, in the long term, is not a planet of fire and ice. It is a planet with slow, gentle, seasonal cycles of extreme length, moderated by an active atmosphere. In 1 year, conditions on the surface of Earth, in the temperate zones, away from the worst volcanic activity, might be survivable. Not comfortable, not familiar, but survivable. The volcanic activity is the critical uncertainty. The simultaneous eruption of every major volcanic system on Earth is not a brief event. Historical analogues, the Deccan traps, the Siberian traps, the Columbia River basalts, suggest that large-scale volcanic episodes can persist for hundreds of thousands of years. The destabilization of Earth's volcanic systems in the stop event creates a legacy of elevated volcanic activity that will persist for geological timescales. But volcanic activity is not uniformly distributed. Between major eruption episodes, there are quieter intervals. The atmosphere has enormous capacity to process volcanic gases over time. Sulfur dioxide converts to sulfate aerosols and eventually rains out as sulfuric acid. Carbon dioxide is absorbed by chemical weathering of rocks, by ocean dissolution, by whatever biological activity survives. Over years and decades, the atmospheric chemical composition will trend back towards something more normal, even with ongoing elevated volcanic activity. The ozone layer, devastated in the first hours, will partially recover. Ozone is produced continuously by ultraviolet photolysis of oxygen in the stratosphere. Sunlight splits oxygen molecules, and the resulting oxygen atoms recombine to form ozone. Without the ongoing chemical destruction from CFCs and other anthropogenic chemicals, all of which ceased to be produced at 0 hour, the ozone layer has a natural recovery pathway. Models suggest partial recovery within years, substantial recovery within decades. The magnetic field is the long-term concern. The geodynamo, reorganizing in the absence of rotational forcing, will not fail immediately. But over centuries and millennia, the field configuration will change substantially. Periods of weakened field, analogous to geomagnetic excursions documented in the paleomagnetic record, will expose the surface to elevated cosmic radiation and solar energetic particles. This is not an extinction-level threat in itself. The paleomagnetic record shows that life on Earth has survived multiple geomagnetic reversals, including periods where the field was significantly weaker than normal. The Matuyama-Brunnes reversal of approximately 780,000 years ago, the most recent complete reversal of Earth's magnetic poles, coincides with no known mass extinction event. Life is robust. It has survived worse. Now let us talk about what human survival looks like in this new world. The survivors who reach the terminator zone, or who are located there by chance at the moment of the stop event, have access to the most resources. Liquid water from terminator precipitation, moderate temperatures, air that, while chemical-laden, is being continuously exchanged by the vigorous atmospheric circulation at the terminator. The architecture of human survival in this world is underground and at the terminator. Think about what this means culturally, technologically, organizationally. The societies that survived the initial catastrophe in deep shelters must now build new infrastructure in an environment with no fossil fuels, all burned or inaccessible, with no industrial supply chains, with no agricultural land in the familiar sense. The soils of the pre-event world have been scoured, buried under ocean sediment, covered in volcanic ash, or chemically altered by acid rain. But the terminator zone has something that agriculture desperately needs: water, continuous precipitation. And as the volcanic winter gradually eases over years and decades, sunlight. Not the sunlight of the old world, 12 hours on, 12 hours off in a steady daily rhythm, but sunlight nonetheless, 6 months of it, followed by 6 months of darkness, in a slow cycle that plants can adapt to, that humans can adapt to. The history of life on Earth is the history of adaptation to changing light regimes. Plants in the Arctic already survive 6-month polar. Animals in polar regions have evolved metabolic strategies for extreme seasonal variation. The biological toolkit for surviving slow light cycles exists. It will simply need to be applied in a new context. Agriculture in the New World will be fundamentally different. Crops that can tolerate a 6-month growing season followed by a 6-month dormancy. Underground hydroponic systems powered by geothermal energy, which is now, thanks to the geological upheaval of the stop event, more accessible and more abundant than it was before. Cultivation of organisms that do not depend on sunlight at all. Fungi, certain bacteria, chemolithotrophic organisms that derive energy from chemical reactions in rock. This is speculative. It is the 15% of our scenario, the alternative theory, the open question, the place where scientific modeling meets human imagination. But it is not fantasy. It is grounded in real biology, real ecology, real agricultural science. The deep ocean biosphere continues unchanged. The hydrothermal vent communities, the chemosynthetic bacteria, the organisms that have always lived in permanent darkness, they are unaffected by the stop event on any timescale relevant to our discussion. Life in the deep ocean has existed for at least 3.5 billion years through every catastrophe Earth has experienced. It will continue. If there is a long-term future for complex life on the surface, it begins at the terminator, underground, in the volcanic warmth of a geologically active planet that has been catastrophically disrupted but not destroyed. Earth has been wounded, catastrophically, permanently, in ways that have erased the civilization that existed before, but it has not been killed. And this brings us to the deepest scientific question raised by this entire investigation. Not how Earth would respond to losing its rotation, but why rotation matters so fundamentally in the first place. Earth's rotation is not an accident. It is the result of the angular momentum accumulated during the formation of the solar system, the same process that causes galaxies to spin, that causes accretion disks to form around young stars, that causes hurricanes to spiral. The spinning of Earth is ancient, primordial, written into the physics of planetary formation, and it has shaped every aspect of life here. The 24-hour day has structured biological rhythms from the level of individual cells, the circadian clock genes, present in organisms from cyanobacteria to humans, documented in Nobel Prize-winning research by Jeffrey Hall, Michael Rosbash, and Michael Young, to the level of global ecosystems. The rotation-driven Coriolis effect has shaped weather patterns, ocean currents, and the distribution of nutrients across the global ocean for billions of years. We evolved in a rotating world. Our biology assumes rotation. Our agriculture assumes rotation. Our civilization assumes rotation. To understand what Earth would be without rotation is to understand with perfect clarity what rotation gives us. Everything. The question we never stop asking. There is one more thing worth saying before we close this investigation. Every scenario we have walked through, every atmospheric calculation, every oceanographic model, every geological consequence is based on real science. The researchers we mentioned are real. The journals we cited are real. The physics is real. We did not speculate beyond what the science supports. We did not invent catastrophes for dramatic effect. The drama was already there, in the equations, in the data, in the models that scientists have built over decades of studying Earth as a system. And that is perhaps the most unsettling takeaway from this entire investigation. Not that Earth could stop spinning. As we established at the beginning, no known natural mechanism could achieve this. The scenario is physically impossible by any force within our solar system that would leave the planet intact. The unsettling thing is something else. It is the realization of how precisely calibrated everything is. How the speed of Earth's rotation, 1,670 kilometers per hour at the equator, completing one rotation every 23 hours, 56 minutes, and 4.1 seconds, is not arbitrary. It is the product of 4.5 billion years of gravitational history. It is slowing, gradually, measurably, as tidal friction with the Moon transfers angular momentum from Earth to the Moon's orbit. In approximately 250 million years, Earth's day will be 25 hours long. In billions of years, if Earth and the Moon survived the Sun's eventual expansion into a red giant, tidal locking may eventually stop Earth's rotation entirely. Not instantaneously, but over geological timescales, with life having billions of years to adapt. The universe, it turns out, is already running our scenario. just slowly, on cosmic timescales, in ways that evolution can follow. What we modeled is that process, compressed into 48 hours. And the difference between a catastrophe and a slow change is not the destination. It is the time available to adapt. Life adapts when it has time. What the 48 hours after Earth stopped spinning really teaches us is not about catastrophe. It is about time. The 4.5 billion years of Earth's spinning history is the gift that made everything possible. Every ocean current that distributed nutrients, every weather pattern that brought rain to forests, every day-night cycle that structured the metabolism of every living cell on this planet. That gift is not permanent. Nothing in the universe is permanent. But it has lasted long enough for something extraordinary to happen on the surface of a small, rocky planet orbiting an ordinary star in an unremarkable. Long enough for life to look up at the sky and ask questions about what keeps it all spinning. And that, in the end, is the most remarkable fact in this entire investigation. Not the catastrophe, the 4.5 billion years before it. Long enough for life to look up at the sky and ask questions about what keeps it all spinning. And that, in the end, is the most remarkable fact in this entire investigation. Not the catastrophe, the 4.5 billion years before it.